Today, I'm just super excited to talk about our work. AppWorld, reliable evaluation of interactive agents in a world of apps and people. This is joint work with many of my amazing collaborators from Stony Brook University, Allen Institute for AI, and Southern University. The talk has roughly like 4 sections, and I will stop off for each of them to take questions. But if you have any quick clarification question, feel free to ask them anytime during the talk. So I want to start this talk by painting a broad vision behind this project before diving into this specific work. Many of us use AI agents that act on our behalf in the digital world. For example, assistants like Siri, Alexa, and Google Assistant are agents that can already do simple tasks like setting an alarm, checking weather, and making a call for us. In the future, I believe these agents will become far more capable. They will be used for doing more complex tasks and will be adopted and integrated even more broadly into our society. There will be Everyone will have their own personalized AI agent through which they will interface with the digital world and to some extent even the physical world. These agents will coordinate with each others and with humans to achieve complex collaborative tasks. There will also be agents that act on behalf of organizations like hospitals, banks, and so on. Their actions will deal with real world resources that will have real world consequences like transferring money, sending medical records, and so on. So as we move towards such a world, it is important to ensure that these agents become more capable, reliable, and trustworthy. The long-term goal of this project is to build a simulated world which acts as a foundation for reliable evaluation and development of such agents embedded into our society. AppWorld is a step towards this long-term goal. And that is what I will talk about next. So AppWorld is a simulated world and a benchmark that focuses on the setting where AI agents individually and autonomously complete day-to-day tasks on behalf of people on their app accounts. So AppWorld includes tasks such as returning an Amazon order and buying a replacement, sending owed money to friends on Venmo, and canceling meeting reminders based on coworkers' emails. So agents can operate apps to do such tasks broadly in 2 ways, either via a browser or mobile user interface or by calling APIs exposed by these apps. At the end of this talk, I'll briefly discuss our ongoing work on agents interacting with the user interface. But for most of this talk, I'll focus on agents calling APIs. Although calling such APIs is the main ingredient, just that is not enough for complex tasks. Here, the calls to the APIs have to be made by writing rich code in an interactive manner. So let me explain it by showing how an ideal agent could tackle an example task. That is, play my shortest Spotify playlist with enough songs for today's workout. My workout plan is in simple note. To solve this task, first the agent has to find the user's workout duration. For this, it gets the user's simple note credentials, logs in, and searches for the workout related notes, all via writing a code snippet, making appropriate API calls to the simple note app. Notice here that the output of the first API is going as an input to the second API. Still, both of these calls can be made into the same code snippet, even without knowing the value of the token variable. This is possible if the agent knows the output schema or type information of the first API and the input schema or type information of the second API. However, what to do next depends on the free-form text present in the notes variable, and so the agent has to print it. The agent finds a node with free-form text indicating day-wise workout durations, and so it prints the current day to find today's duration. Now notice here that the agent printed today's day because it found a node with day-wise workouts. However, the user's nodes could have been organized in many different ways, each of which would have required a different code snippet. For example, if there was a node with month-wise workouts, the agent would have printed the current month instead. So this means that here the second code snippet had to be written interactively based on the first code snippet's output. All right, so now at this point, the agent knows today is Tuesday, so it infers a 45-minute workout and then searches for the shortest playlist with enough songs for that duration. To do this, agent has to loop over the playlists, find total duration for each, and filter and select them accordingly. Doing this involves writing rich code with various programming constructs like loops, conditionals, arithmetic, and so on. So, in summary, we saw that a seemingly simple day-to-day task can be quite complex, and it had two key requirements. It required environment interaction to write the next code snippet, and the code itself was rich with various programming constructs. The key question we ask in this work is, how can we develop and benchmark such rich and interactive coding agents for complex digital tasks in a rigorous and reproducible manner? To do this, as it will become clear later, we need three ingredients: a realistic and reproducible environment of API operable apps for agents to interact with, a benchmark of complex tasks requiring API calls with rich and interactive coding, and a robust programmatic evaluation framework for checking agents' code completion. Now, there have been many existing tool use benchmarks like Corilla, Toolbench, API Bank, and many more, but they do not support these three requirements. Their tasks are simple with only a linear sequence of 1 to 4 API calls. They have a small number of API implementations or use unstable APIs. And they use human or LLM judgment or reference based evaluation, which is not robust for complex tasks that have many solutions. To bridge this gap, we introduce AppWorld, a world of apps and people. It constitutes a new environment, a challenging benchmark, and a robust evaluation framework. Next, I'll talk about these three components, starting with the environment. We want to create an environment of API operable apps like Amazon, Gmail, Venmo, and so on. We want this environment to also support reproducible experiments, complex tasks, and robust evaluation. Reproducible experiments require resetting the start environment to identical state whenever we want an agent to run on that task. Complex tasks require tailoring the start environment specifically for the task to be compatible and challenging. And lastly, robust evaluation requires accessing the final environment state, as complex tasks can be solved in many ways. So this means that to satisfy these requirements, we need full control on the state of the environment, which for an app-based environment is defined by the databases underlying each of these apps. So in other words, we need full control on the app databases. Now, this rules out the option to build this environment from real apps implemented by the companies because their proprietary app databases are fully controllable only by them and not by us. So we instead implement simulated versions of these apps in our own backend of APIs and databases, which provides us or anyone with full control on the app databases. Simulated apps also provide other benefits over real apps. The real apps require real resources. For example, a Venmo payment needs real money, whereas in our simulated Venmo app, it is just a database entry indicating who paid whom what. Simulated apps are also fast, always up, and have no rate limits, which is not the case for real apps. But all of these benefits of simulated apps are not enough. We also need the richness, realism, and complexity of real apps. And to do this, we have spent huge amount of effort in this work, making these apps to be super rich and high fidelity in nature, meaning that they have closely similar features and behavior to the real apps. Our app implementation span over 60,000 lines of code, 457 APIs with detailed documentation, and 100 plus database tables. Our apps have fine-grained and detailed functionalities. For example, the Gmail app won't be just send and read emails as it is in real life. Emails will be organized in threads within your inbox and outbox. You can reply and forward individual emails from them to different contexts. You can schedule them for a future time. You can manage your drafts, attachments, labels, to search over them, and a whole lot of other things. Actions or API calls in these apps also lead to realistic in-app and cross-app consequences. For example, when you place an Amazon order, your cart is cleared, the product inventory is updated, your payment card is debited, it shows up in your past orders with tracking information, and then you also get an email confirmation with a receipt as an attachment. These apps also have authentication privacy features like login, sign up, forget and reset passwords, and so on. And they prevent access to others' private information as well. And these APIs also provide informative error messages and never blanket errors like internal server error. For example, if the agent tries to send money to someone via a payment card that does not have enough balance, the API will respond with a message saying so. This allows the agent to learn by interaction. These apps also have been extremely rigorously unit tested. We have over 1700 plus unit tests spanning 34,000 lines of code and providing a test code coverage of 98%. We want the agents to be able to explore this environment arbitrarily without the environment breaking or behaving unexpectedly. This rigorous testing gives us high degree of confidence that we have such a reliable environment. And as discussed before, these apps also provide full programmatic control over the database state. And we use this control to populate these app databases with rich and realistic data. As I will show later, this data will help us build complex tasks. In particular, we create a simulated world of 100 plus people. In this world, each person has their own personal accounts on all apps. They also have a home and work address for online delivery and payment cards for monetary transactions. This allows for personal tasks like buy a t-shirt for my home delivery using my Visa card. These people are also related to each other in the world via various relationships like parent, friend, sibling, partner, and so on. This allows for relational tasks like email my partner that I'm running late. These apps are also populated with personal and interpersonal digital activities of people which are consistent with their relationships. For example, on the top, you see an employee sending an email to his manager asking for a leave approval. And on the left, you see two roommates chatting about apartment bill payment over phone, and so on. These activities are populated spanning 2+ years of time, which allows for temporal tasks like delete my emails from last year. Overall, the resulting database has 100 plus tables, 350K plus rows, and 750 plus columns. Note, this data is generated. So I don't have time to go in much detail here, but note that this data is generated procedurally by sampling from human in the loop LLM generated data as opposed to by people simulated via LLM agents. The resulting world of apps and people, which we call base world, provides us with a rich and realistic foundation to build complex tasks on top of. And I will show how we use it later in the benchmark section. So next I'll talk about the benchmark, but I can also pause here to see if there's any question. Okay. Okay, so next I'll discuss how we construct the appworld benchmark and specifically how we design complex tasks. So for this, we start by writing day-to-day scenarios, which naturally require rich and interactive coding. Here, a scenario is an ungrounded blueprint for the task. For example, buy the product that my related person suggested someday. From the scenario, we can Create multiple tasks like buy the shirt that my roommate suggested today, buy the desk that my coworker suggested yesterday, and so on. Now remember that we want the agents to follow this instruction by taking actions in the environment. So the instruction alone is not enough to define a task. We also need a world state, which constitutes the database state and current time within the world. And we also need a supervisor, who is the person in the world on whose behalf the agent is supposed to operate apps. For the task to be solvable, we need the instruction, world state, and the supervisor to be compatible with each other, meaning that all conditions required to follow the instruction are satisfied in the world state for the supervisor. For example, in this task, today is 11th of February and the supervisor is Alice. Here, as per the database, Alice's roommate has suggested her to buy a Nike shirt today via a phone conversation that you can see on the left. This Nike shirt is available now on Amazon, and Alice has enough funds in at least one of her payment cards to make the purchase. These conditions make the task to be solvable. However, mere solvability is not enough. We also want tasks to require thorough reasoning to solve. For this, we include distractors, hurdles, and task variations. Here, including distractors means making it so that bypassing any reasoning step will likely mislead the agent to the wrong path. For example, here Alice will have short suggestions not only from today but also from days before. So if the agent ignores the word today, it will likely fail to identify the correct shirt to order. Similarly, there will be other distractors as well. If the agent ignores the word shirt or roommate, it will also similarly get distracted. Next, we also include task hurdles, which require agents to do realistic failure handling and adaptation. For example, here one of Alice's payment cards has no money in it. So the agent has to realize to try another card when that one fails. And lastly, we also include task variations, which require agents to reliably solve tasks under slightly different or contrasted conditions. For example, remember we created this task by grounding the scenario. Similarly, we can create a different task by differently grounding the same scenario. Notice that the two tasks have different current times, supervisor, placeholder values, and the database states. Note that these task variations are always carefully designed to also catch the shortcuts that distractors cannot. For example, on the left, the key relevant suggestion has come via a phone message, and on the right, it has come via an email. So the agent needs to check both email and phone for suggestions to succeed on both the tasks. All right, so now that we know what we want from these tasks, let's see how to ground the scenarios into tasks so that they satisfy the required initial conditions. To do this, we use the base world that we discussed earlier. Remember that this world already has a rich, fully populated app database, including people and their activities. This world provides us with a reusable foundation that can be used across scenarios. However, it does not satisfy task-specific requirements. We will need to adapt the base world for each task, as I will show in a bit. So, to ground the scenarios, we need two things. We need to select the placeholder values like shirt for a product, roommate for a related person, and so on. And we also need to satisfy the required initial conditions. Now, some of these conditions can be satisfied by doing a search in the app databases of the base world. For example, to find a compatible supervisor, we can find a person in the world who has roommates. But for other conditions, search is not enough. Instead, we need to edit the app databases. For example, the base world doesn't have a phone conversation about the shared suggestion between Alice and a roommate. So we need to create one by editing the app database. Now note that this is a simplified picture. In practice, there are many conditions, often interdependent with each others. So for having the flexibility, we do all of this programmatically by writing the task setup code for each and every scenario. All right, so now that we have the tasks, we also want to programmatically guarantee that they are indeed solvable. So for each task, we also write the solution code and evaluation tests, and then programmatically verify that running these solutions passes all evaluation tests. Now, note that here I want to emphasize that each task scenario poses unique requirements. So all code really has to be written individually for every scenario, and it has taken over 5+ hours of time for each scenario and over 40,000 lines of code overall. To maintain high quality, all scenarios and code have been developed by us. It's not crowdsourced, and they have been reviewed multiple times by multiple people. And here are some more sample tasks from Apple. I'll go over a couple of them. The first one is I'm going on a camping trip with my siblings. I email them a checklist of the needed items, check who committed to bring what, then order the remaining items on Amazon. And the second is I booked a few hotel rooms today for my upcoming trip. How much did I spend in total from my Visa card based on the email confirmations? And so on. All right, so now to solve these tasks, the agent is given an instruction, the API documentation to understand how to use these APIs, and an interactive coding shell with an API client. For example, via this shell, agent can log into Spotify, explore API documentation interactively, or obtain supervisor's personal information. By default, we provide an IPython-based shell, but one can really use any language or HTTP client of their choice. Based on our written solutions, we find that the appworld tasks are quite challenging. They require 1 to 4 apps, 5 to 25 unique APIs, and to 10 to 200 API calls, and 20 to 130 lines of code. All of this is assuming our perfect knowledge of APIs. In practice, agents require many more API calls and lines of code as they learn by interaction and exploration. We have 750 tasks built from 250 scenarios overall. Now remember that each task scenario can have multiple apps as shown on the left. From across all the 9 apps which are available, we hold out 2 apps, Amazon and Gmail. And all tasks involving any of these 2 held out apps are moved into the test challenge spread. And the remaining are randomly divided in the train, dev, and test normal splits. Now notice that we have 2 test sets, test normal and test challenge. From these, the test challenge is our main test set, in part as it forces learning to use APIs for held out apps, reading and understanding the API documentation. Additionally, test challenge also has inherently harder tasks as well. So next I'll talk about evaluation, but I can also pause to see if there is any question here and take it so. Okay, all right. So now that we have the tasks, we need a way to robustly and programmatically evaluate agents. Now, agents can solve such tasks in many ways. For example, they can download the Amazon receipt from its API or its email confirmation. Both are completely valid. So comparison to a reference solution cannot be used. Therefore, Apple uses a state and execution-based approach. In particular, the agent starts with an initial database state associated with the task. The agent makes series of code executions and we get the final database state. We compute the difference between these database states to obtain cumulative changes that the agent has made to the tables, rows, and columns. And then we programmatically check whether they include all desired and no undesired changes. We do these checks roughly in a hierarchical fashion, going from tables to rows to columns. For example, for our task about buying a shirt on Amazon, we first check that only a small list of tables has changed, namely Amazon orders, inventory, and so on. Now, this very simple assertion captures vastly many ways an agent could have made undesired changes or collateral damages for us. For example, if the agent initiates an Amazon order return when it was asked to buy something, the Amazon returns table will change and this test will fail. We then check that only €1 has been added to the orders table, and then this order has only the expected Nike shirt and nothing else. So the takeaway of all of this is that regardless of what path the agent takes to make the desired change, it will pass. And regardless of what undesired change the agent makes, it will fail. All right, so now using these assertions, we define two evaluation metrics. The first one is the task goal completion, which checks that all tests in a task pass. And the second is the scenario goal completion, which checks that all tests for all three tasks in a scenario pass. All right, so next I'll discuss the experiment. For this, we benchmark agents built from open and closed LLMs by carefully adapting four strong few-shot prompting methods. First is React, which I'll talk about in a bit. Others include plan and execute that adds a planning stage before React. Function calling that leverages native parallel function calling ability of language models, and full code reflection that attempts to generate full code for the task, and if needed, retries by reflecting on the error stack trace. In interest of time, I will only explain the overall best performing method, which is React. The React first generates a natural language sort about what it wants to do, and then follows it up with a code snippet to do that. Depending on whether the code execution succeeded, the environment prints an output or an error stack trace based on which the agent decides what to do next, and the sequence repeats. So now let's see the results. Here, the x-axis shows different open and closed LLMs, and y-axis shows the task completion score on the test and normal spread. Here, the score refers to the maximum score achieved by that LLM across four few-shot prompting methods. We see that the GPT-4o struggles, getting only under 50 points, even in this easiest setting, and other LLMs are much farther behind. Next, let's see the robustness of these agents. Remember that our scenario goal completion captures whether agents can reliably complete all three tasks of a scenario, which are variations of each other's. We see that going from task goal completion to scenario goal completion, all scores significantly drop. For example, GPT-4o drops by 17 points, going from 49 points to 32 points. This shows that indeed agents do not complete these tasks reliably. Furthermore, when we go from the test normal to test challenge, which is our main test set, all scores significantly drop further. For example, GPT-4o only gets 13 points in the scenario goal completion. And when we break down the GPT-4o numbers into individual prompting methods, we find that the React agent works the best and others are behind it. We have, in this work, we have developed tasks in three levels of difficulties, which allows us to analyze how the agent scores change with increasing task difficulty. Here, the histogram is showing the distribution of tasks as per the difficulty levels. And the lines show the task goal completion scores for different prompting methods. We see that the best scores drop from close to 55 to close to 20, going from level 1 to level 3, indicating that agents struggle much more on harder subsets of Appworld. And we see similar trend for other indicators of difficulty as well, like number of APIs and lines of code as per our written solutions. And finally, based on manual error analysis, we find that agents make various mistakes. They make incorrect assumptions about the environment without looking into or interacting with the environment. For example, in the Amazon task, the agent assumes the suggestion has come via a phone message and doesn't check the emails and hence fails. They struggle to adapt based on errors properly. For example, on placing the Amazon order, when the environment says the payment card doesn't have enough balance, it gives up instead of trying another card. They forget state because of long trajectory. For example, the React trajectories are often more than 35 steps long. They also use APIs incorrectly, ignore crucial pieces of instruction, and make various kinds of coding and common sense errors. So next I'll talk about some ongoing and future work, but I can also pause here again to see if there's any question. All right. Okay, so next I'll talk about some ongoing and future work. So as we have seen, solving actual tasks require many skills like writing code as per documentation, interacting with the environment, dealing with long-range dependencies, and so on. Apple provides a rich and flexible development environment to explore research methods for learning these skills. These skills are also applicable to complex tasks in other domains like science and software engineering, but they are harder to acquire in the available environments. And to acquire these skills, And to acquire the skills and make progress on Apple, there are many research directions one can pursue, like learning to self play on the Apple environment, training language models on interactive coding with API calls, learning a high level skill or function library, and exploring planning based, search based, and memory augmented approaches. And soon, all of this research will also be doable in a multimodal version of AppWorld. So far, I have talked about agents calling APIs, but sometimes apps do not expose public APIs. So agents should also be able to interact with the browser and the mobile user interface directly. In this work, we implemented many API operable apps via our backend of APIs and databases, which can be operated with an API or HTTP client. In the follow-up work, we have also created browser and mobile user interfaces for all of these apps. The UI is closely similar to the real apps, and it is backed by the same backend of APIs and databases. So now the agents can operate over all modalities to solve Apple tasks. And since Apple tasks and evaluations are database state based and process agnostic, they can be reused as is. And now finally, let me take a step back from what we proposed in this work and revisit the broad vision I started with to lay out the future work. We envisioned a future where AI agents will get deeply embedded into our society, taking various roles and responsibilities. In such a society, agents will have to collaborate with other agents and humans to achieve complex collaborative tasks. They will have to work in messy real world environment that require dealing with failures. They will have to be resourceful, making sure they are not wasting your time, money, and other resources. And because real world resources are involved, they will have to be robust to inevitable security attacks. And after all, agents will have to deal with people, so they will have to be socially intelligent and fit into our social norms and expectations. Apple provides a fully programmatic, controllable, and extensible society of people and their digital activities. This foundation can be used to develop and evaluate agents in all of these directions. And if you're interested, please reach out and I'll be happy to chat further. All right, so in summary, we have introduced AppWorld, which was born out of a significant engineering effort by our team, writing over 100,000 lines of code. We have developed a rich and fully controllable app environment with simulated activities of people. On top of it, we developed a benchmark of complex tasks with robust programmatic evaluation framework and showed that best LLMs struggled on it. And we discussed any future works that Apple can support for building better agents and new agent benchmarks. So please check out appworld.dev for Task and API Explorer, Playground, Leaderboard, agent trajectories, and a lot more. We have made Appworld to be very easy to use and fast. You can just pip install it and quickly start building and testing your agents. And if you have an agent, the code on the left is all you need to run and evaluate it on Appworld. That's all I have, and I'm happy to take any questions of this.